Welcome to our study of college algebra. College algebra is really obsessed with this focus on functions and how those functions behave, whether that function is a graph, whether that function is an expression, or whether that function is a table. And we're going to look throughout this course at how those things all can be manipulated and worked with, and what we can learn from how those functions can model real-world situations. We're going to start off with an introduction to functions and function notation in section 1.1. And to do that, we're going to start off with a couple of definitions that will be helpful to us. The first definition is probably the most important. It's the definition of a function. Now, a function is any relationship or any rule where each input results in one output. Visually, what this is talking about is we're going to have this thing, maybe I'll call this my function machine. And we're going to put an F with an X in parentheses on the function machine to label it. We'll talk about why in a minute. But the idea is this machine follows some rules. So if I took the number 3 and dumped it into this machine, the machine will dump out some type of output, maybe the number 5. So the idea is I've got inputs on the left that go into the function and something happens and come out as outputs on the right. So let's say, for example, I took the number 2 and I threw the number 2 into the function. What's going to come out of the function might be the number 6, just for example. The key relationship or the key aspect or quality of a function is if I were to take the number 3 and throw it in again, the function machine is going to give me the same answer it got last time I threw a 3 into the function. It's going to give me a 5 again, because if I throw a 3 in one time, I'm going to get a 5 out. If I throw 3 in again, I get 5 out again. It's a rule that's going to always give us the same result. Now, that doesn't mean that I can't repeat a result. I might throw the number 7 in and something happens and it throws out a 6. Notice throwing the number 2 and the number 7 in both threw out the number 6. And that's okay with a function. What's important with a function is what happened with this green and pink example is when the number 3 went in twice, it gave us the same answer both times. That is the key rule of a function. The second key definition we need to be familiar with is a special type of function that is 1-to-1. Now, a 1-to-1 function says that each output comes from one input. And now, this is different than the example we just saw. The red and the brown numbers, when the 2 and the 7 went in, they both gave us the same output. That means the output of 6 came from 2 different inputs, and that is not allowed if the relationship is 1-to-1. So if I've got my function machine here now, and we've already thrown in the number 3, and let's say it gives us the number 5. Then we throw in the number 2, and it's going to give us the number 6. Now if I throw in the number 7, though, 7 cannot give me a number that's already come up before. It has to give me a unique number. It's 1-to-1. Every 1 has 1 answer. So maybe this time it gives me an answer of 9. Every output came from a unique input. That makes the function 1-to-1. Now, there is some notation we want to be familiar with on a function. The idea of a function notation that we want to be familiar with is we'll use some letter to name the function, usually F for function, but we can change that letter if we want. And then in parentheses, we're going to put the input of what goes into the function. So that input is going into the function machine, and that's going to equal the output of the function. So for example, let's say the number of police officers which we'll represent with the capital letter N, on the streets of a town in a given year. And we'll use Y to represent the year. Well, there's a function relationship here. We could say that we take the function and we put in the year, and that should give us the output. The output is the number of police officers. So for example, the function of 2021 might equal 200. In other words, what that's saying is the input is 2021, that's the year, and the output is 200, that's the number of police officers. In 2021, there were 200 police officers. That's the idea of function notation. It doesn't mean F times Y. It means F is the function machine, and that number Y, whatever number is there, is put into the function to give us some output. All right, let's start talking about ways we can express a function. One common way we express function is as a table. And here we're going to give each row or column the input and the output. So for example, we might have a function of months is equal to the number of days in that month. So I'm going to have a table with the months and days, and it's going to list some of the possible results. Well, in the first month, there are 31 days. In the second month, there are 28 days. In the third month, there's 31 days. In the fourth month, we know there are 30 days. What's interesting here is I can see that this is a function because each one of these inputs has only one output. The month of January always has 31 days. The month of February, we're going to say in a non-leap year, always has 28 days. If we had to adjust for leap years though, it would not be a function, but we're talking about a standard year here. But this function is not a one-to-one function. And the reason it's not one-to-one is we have multiple months that have the same number of days. Because we've got a repeat in the days with different months, that's not a one-to-one function. Let's write a function based on the number of customers in the store, and we want to write it as equal to the number of items sold. Is that a function? Well, let's look at our customers and items sold, and we'll make a table. Let's say when there were 3 customers in the store, 8 items were sold. The next hour, there were 5 customers in the store, and there were 7 items sold. The next hour, there were 3 customers, but 30 items sold. Then there were 3 customers and 6 items sold. Later, there were 9 customers and 4 items sold. Is this one a function? Well, this one is not a function because we see that twice there were 3 customers, but it resulted in a different number of items sold. So this one is actually not a function because the number of items sold is not determined by the number of customers. The same number of customers could buy a different number of things. It's not a function. And it can't be one-to-one because it has to be a function first to be one-to-one. Let's look at one more option. Let's look at a function of hours to give us maybe a distance traveled. So we're going to have the table hours and distance. Oops, wrong color. So we're going to have the table hours and distance. We're going to say after 1 hour, 10 miles were traveled, after 2 hours, 20 miles, after 3 hours, 30 miles, after 4 hours, 40 miles. Well, what we see here is each hour has a unique number of distances that it travels. So the hours does determine the distance. It is a function. Because we didn't have the same hours giving us two distances, each hour determines its own distance. It is a function, but it also is one-to-one as well. Because in this case, each distance was correlated with a unique hour going backwards. There were no repeats, so this is a one-to-one relationship. So that's kind of how tables can be represented as functions. But really important to this course, we're going to look at not just tables as functions, but we're going to look at graphs as functions. The idea is that a graph with our xy plane let's say I've got a graph that is going to come through these points, let's say. So it's going to come up, bend, down, and up. And let's put another point on it here. The way we can determine if a graph is a function is we're going to use what's called the vertical line test. And that determines if it's a function. The idea is if I were to draw a vertical line through this graph, this vertical line can move through the graph and it's only going to touch the graph once at any given point for that vertical line. If it only touches the graph once, then we can say that it is a function, because that vertical line only touched the graph once. Now, if I want to know if it's one-to-one, we use what's called the horizontal line test. And that will tell us if it's one-to-one. The idea here is I can draw a horizontal line through the graph. And then I can move this graph up and down. But the horizontal line can only cross the graph once. If it crosses the graph more than once, what we see is there's more than one option that gives us that horizontal value. That tells us that it is not a one-to-one function. Let's look at a few more examples. Let's look at this function here. I'm gonna put a point here, here, and here, and I'm gonna come up slowly, level off, and then take off. On this graph, what I can see is I can draw a horizontal line. So let's do the vertical line test first. Vertical line test. Is it a function? Draw a vertical line, and you notice the vertical line's only going to touch the graph one time. It doesn't cross the graph multiple times. Because it only crosses the graph one time, we can say it is a function. What about a horizontal line? If I were to draw a horizontal line on this graph and move it around, it's only going to touch the blue line one time, each horizontal line. Because it only touches the blue line once, we also say it is one-to-one. Let's look at a third graph. let's take a look at this graph, which is going to be a circle. Now with this circle, if I were to draw a vertical line through the graph, notice the vertical line crosses the graph in 2 different points, up at the top and down at the bottom. When it crosses the graph at 2 different points, we say it is not a function. Not a function, because it crosses the graph twice, that's not allowed. Now, one thing we might be interested in is how we can evaluate a function. So I want to scroll back up to our table that we use. Let's look at the hours and the distance. We can use this table to pull information off the table to interpret. I could say, we can say f of, and stick a number in there, f of 3. What that means, I want to know what the function gives us at 3 hours, because 3 is the input. And I can look at the graph really quickly and see at 3 hours, 30 is the output. So we can evaluate the output for a given input. I can also say, what is the hours when the function gives me an output of 40? Well, I can look at the graph and I see an output of 40 corresponds with an input of 4. So those hours, the input, are equal to 4. And that's how we can use a table to pull information out to interpret our function notation. We can do something similar with the graphs. Scrolling down to our graphs, taking a look at this first graph on the left, problem number 1 here. If I wanted to pull values off of the graph, the x's represent my inputs and the y's represent my outputs. So I could say, what is f of 1? In other words, when the input is 1, how far up or down did this graph go? Well, this graph didn't go up or down any, it's got a y value of 0. I could ask for f of 0. So that means starting at 0, this graph goes up 2, the output is 2. I could even say, what is the x that gives me an output of -2? Well, if I look at the output of -2, that's going to hit the graph right here. What's the input there? -1, -2, -3. So x, the input, is -3. And so similar to how we can pull information off of the table, we can pull information off of the graph to determine our inputs and our outputs. But probably the most common way to do this comes from looking at formulas as functions. So for example, we might have the formula that the height of something is related to this input of p, and then it's going to give us an equation that uses p. P squared plus 2p, for example. Now I can evaluate what is the height at 2. Actually, let's do the height at 4. What that means is 4 is going into the height, or the h function. The function has p's in it. So every one of those p's is going to be replaced with the 4 of the input. So we end up with 4 squared plus 2 times 4. Order of operations tells me to evaluate the exponent first. Then I can evaluate the multiplication. Then I can evaluate the addition to get 24. Let's plug another number in. Let's plug a negative in. Let's find out what happens when -2 is the input on our function. Well, again, the p's are going to be replaced with whatever went into the function with the -2. Order of operations again, squaring a negative makes it positive. Then we do our multiplication. And then we can do our subtraction and we find out the output at -2 is going to be 0. Now, there are lots of functions out there that exist. We are going to, in this course, though, refer to some specific functions along the way that are known as our toolkit functions. And these toolkit functions are in your textbook on page 12. So make sure you take a look at these functions and how they work as a table, as a graph, and as a function. There are several toolkit functions. Now, I'm going to list the name of the function, the formula of the function, and the graph of the function. And this is all on page 12 in your text as well. But we've got linear functions, which are f of x equals x, and the graph of these looks like a straight line going up diagonally. We have quadratic functions, which are f of x equals x squared, and the graph of a quadratic function looks like a U. There's cubic functions, which is f of x equals x cubed, and the graph of which comes in from the bottom, levels out, and takes off. There are reciprocal functions, which is f of x equals 1 over x. And the graph of this actually looks like a curve in both the first and third quadrants. There are reciprocal squared functions, and that's where the 1 over x is squared. If we do that, the graph moves into the first and second quadrants. Another graph we might want to know, another function, is the square root, which is f of x equals the square root of x. And that function starts at 0 and just comes up with a curve. There's the cube root function, which is f of x equals the cubed root of x. And that one, it's kind of like the cubic, but it comes in from the side and goes out on the side. And then finally, the last one we're going to talk about here is the absolute value, which is f of x equals, and we put vertical lines around x, meaning the absolute value of x, and the graph of this one is a sharp V shape. These are going to be some toolkit functions we're going to use as this course develops. It's going to be useful to be familiar with them. They're listed on page 12 of your text, so you can look at them closer. But these functions are going to really help guide us as we continue to study functions, how they behave, how they're graphed, and how they can model the real world. I think you're ready to take a look at the practice problems for lesson 1.1. Good luck as you take a look at those.